And I am going to share my screen. I'm going to share this screen. Does everybody see a shared screen?
Yep, we do. It's a
Okay.
little small. I
All
don't
right.
know if you
Yeah,
can make it any.
yeah, I can bump that up.
Yeah, that's great.
And
Yeah,
we'll
that's
bump
good.
this up a little bit. So one thing that is, all right. So how many teams do we have on? I see 12 participants.
Yeah, I don't know how many are represented from each team.
Yeah.
Since we're recording this, a lot of teams might not show up. This might
Yep.
not be a good time for them, so don't worry
All
about
right.
that. Yep.
All right. So my application is called 3D MHD. It's a three-dimensional magnetohydrodynamic model, which is a fancy word for a fluid dynamic model with magnetic forces as opposed to just fluid forces. Um, it is a model that simulates the interactivity of fluid forces commonly found in stellar objects. And these would be plume and filament development inside a star. Uh, that has to do with, if you're familiar with like solar flares and a phenomenon like that, that have a magnetic component to how they form and how they move inside the star. Uh, so that's what this simulation does. It simulates this interactivity of plume development inside a stellar object. It was written by Dr. Mark Rast at my lab, the Laboratory for Atmospheric and Space Physics, and it's been widely used for various studies. Um, it's a pretty simple code. It's all written in Fortran, and let's see if I can pull the Git repository over so you can see it. So I'm assuming I haven't seen. Nobody's emailed me, and my email is in the Git repository. But let me slide this over. Uh, it's very simple. It's all Fortran. It's an MPI code. Um, there is a very good description of the simulation in the PDF and build instructions, output expectations, things like that in the README. Uh, so you can pull this with a Git clone, and you can build it on a Linux machine. The model that is the standard build when you do a Git clone is a 24 core model. So it's a 4x6. So there are two main files that you'll be expected to edit. Right? So you can look in the right pane on the screen. These are the files that'll get pulled down, these .f files. The two main files that you're going to work in are the 3DMHD param file, this one here, right? And this will set parameters like your processor spread. So you'll see here, this is a 24 processor. It's spread 4x6. The grid size, right? Because we're doing a fluid simulation over a three-dimensional grid volume, right? And so this is where a lot of the parameters that we will be setting to determine your complexity of the model that we're going to ask you to run, they will get set in here. A couple of things about this simulation and how we will expect you to run things. We will have a series of simulations. I'm going to choose a number. It may be maybe more than this, maybe less than this, but we'll give you 5 simulations to run, and they will range in complexity. There may be very simple ones, just a couple iterations with a fairly conservative grid size, and it may only take a few minutes to run. And if we give you 5 simulations, the first one will be easy, second one will be a little bit more hard. One of them might not be doable at all on your cluster, and they will range from easy to hard in that spectrum. And you'll have to have an understanding of the simulation enough to know, hey, I can run this one, I can't run that one. So part of this challenge is how do you schedule the workload? And how do you analyze the simulations and tell, hey, with all the jobs that I have to run, this is how I should prioritize processing through my workload. So that's what we'll do. We'll hand you a number of simulations to run. This code is, when we run it in the lab, we've not converted it to GPU code. So I think, Jeanette, is there still an expectation that they can run this on GPU if they can convert it?
Yeah, so the good news is I just talked to Lenaro about getting the ARM profiling tools, which I don't know what they're called now, right? But they're basically parallel profiling tools. And each team will have 64 seats, so they can do a 64 core analysis, profiling analysis. So yeah, you could analyze the code using those tools and then determine places where you might want to port that to your accelerators. And so that's a possibility in this challenge, is to improve the code and maybe GPUify it or whatever accelerators you might bring. That would be an interesting thing here. And then the way that would work is you would share your improvements with the committee. We'll keep those private for the competition, and then after the competition, we reserve the right to socialize those changes, particularly with Doug and the writers of the code. So, but that should be a thing. Should have profiling tools and everything. That should be early next week. We'll get those licenses in teams' hands and some instructions on how to download the profiling tools and install them.
Okay. Now the second file that you'll spend some time in is the 3D set file, and this is where things like where your files are going to get stored and how often you dump files out uh, for time stepping and things like that. This is where those things get set. This is the file name structure up here. This will likely change. This was a default from an older run. It's just a string of characters. There's nothing special about it. In fact, I think I've changed it in some of the test runs that I've been doing. Iterations, right? So how often, you'll see these are all commented up here, right? So the total number of time steps we're going to ask you to run, and the total number of how often we want you to dump out your data. Those are some settings that you may want to play with. This simulation in its larger forms will eat up some hard drive space. So I would suggest that you have on the order of half a terabyte to a terabyte of free space. We're not going to, my models alone isn't going to use all that, but I think that's a safe boundary. I think most clusters, most people have had at least that. So, all right. So compiling this, it's a pretty simple make file. All right, this one I'm compiling with the GNU compilers, but it runs with the Intel compilers, GNU compilers. Those are the two that I have access to on my clusters, so that's what they've been tested with. GNU is free, so I assume everybody as a baseline at least has access to the GNU compilers. This code is a little bit old. It was written in the late 90s originally, early 2000s. It's written in Fortran, so because of that, there are some things about formatting and Fortran stuff that we're using in the GNU compilers, we're using some legacy flags. I've commented out most of these because I don't need them with my environment, but you may need to uncomment these to point to your MPI libraries, right? And you may want to play with various compiler flags for optimization. And those are all dials that your teams will need to play with for your environment. It builds this executable. This is what actually gets run in your job script or from the command line, whichever. If you're you're building this over and over and over, and you do a make clean, then it's going to execute this and clean everything up to so that you can build it again, so you don't have any leftover object files, and it will recompile, relink everything in a clean manner. So now, if you can tell on my left-hand window over here, our cluster, the semester has started. So all of a sudden, our cluster is fully subscribed. I have submitted a couple of jobs, and they're still in the job queue pending. However, I sort of anticipated this, and we're going to switch over to a run that I previously did this morning, or actually earlier. Let's go here. Right, so when the model runs, we're gonna, if you're running with a scheduler, you'll have, this one's a Slurm system, so you'll have some kind of a scheduler job script, right, that will likely look something similar to this. We're running, this is a 24 core run, 24 process run. For my cluster, that's one node, partitions, all these types of things. But down here, for us, we're using modules. It'll load the appropriate MPI libraries and everything. But here are the two important things. It's important that you be in the directory where you're going to run, because it's going to dump all of its files in that directory. So this is a 24 core run, so there are 24 of these files, 0 to 23. These files are going to get updated per iteration, per how often you tell it to dump its variables. So it's quite possible that they'll grow if we're dumping the variables every iteration, every 10 iterations, whatever. And I tell you that you're going to do 1,000 iterations of the simulation, right? So you'll want to make sure that if you're going to run it multiple times, that you are in the appropriate directory. Otherwise, you risk overwriting your files. If you're running two of these simulations at once, you just want to make sure that you're running them in their own directories, right? This is the actual execution, right? So I'm running it with MPI run. I'm calling for 24 processes, and I'm giving it this executable, and away it goes. I don't know how many teams are running with schedulers and without. It might be that we also stick a time statement in here, so we capture an external wall clock time for performance, but that doesn't affect the execution of the model. In fact, basically it's a matter of sticking time right in front of this command. So that command would look like that. But other than that, that's pretty straightforward. Now, these files, it's dumping all of its variable information typically every iteration. So if you run a 64 process simulation, there's going to be 64 of these files. So that's why I say you got to watch out if you may need to change how often it dumps its variables. If it's one-to-one, these files can grow very large. We will tell you in the simulation when we give it to you what things you can or can't change, right? So sometimes it's okay to change how often it dumps its variables. There may be an instance where I say, hey, don't change this. You know, as a part of the challenge, we want to see uh, that's just a factor in the challenge. But we will tell you which variables in the simulations you can or can't change. How you distribute them on, you know, how many processes you run with, how you distribute them on your cluster, optimizations in the build, those are all up to you. Whether or not, you know, whether or not you want to dump the variables at all may also be up to you, right? Dumping the variables does take time. It does take disk space. You can restart the model and start from a given time step. So you can checkpoint the model in case your computer, your cluster crashes in the middle, and you need to restart it without losing a lot of compute time. You can checkpoint it and start from a previous time step, and that's why in this file right here. That's why this is important, because it does use this uh, to determine your checkpointing file structure. So I'm blabbering on a little bit. Are there questions? Feel free to interrupt me.
There is one question that has been sent to me. So will the teams need to keep and submit all of the output files?
No, and in fact, what will need to be submitted will be, if you're using a scheduler, I want to see the output file from the scheduler. I also want to see the I believe it is this file right here. This file here gives me results, right? I need to verify that these numbers are correct. And then it also tells me your iteration information and simulation time.
And then
Sorry, I got kicked off of a node. I gotta get back to it.
oh, sorry. I'll give you a second here.
All right.
So my other question is, what's the input? Like, how do you have different inputs?
So the simulation is self-contained. Some of the inputs are what forces we decide to give you and the grid size we decide to give you. It's a straight numerical simulation, so I may adjust the initial conditions, but they will be constants in the simulation. You won't need to change anything. You'll just need to compile and run. So there's not like in many models you have an input deck or an input file that are initial conditions. These are all hard-coded into the source. Does that answer your question?
Yep. Great, thank you.
Right, like I said, on the order of high-performance computing codes, this one is relatively simple. There's not a ton of math beyond entry-level differential equations. I think everybody got at least a couple of fluid dynamics mixing problems in your undergrad differential equations class. Uh, that's this kind of simulation. Although instead of some of the normal forces that you'd be used to in a typical mixing problem of thermal forces or gravitational forces, there are also magnetic forces and some gas physics in here that are a little different. But we're not going to ask you to really dig into the math. Let's see, where was I? Oh, simulation time. This is what I'm going to be looking at to verify results and to look at performance in conjunction with your job script output file, which I don't know if I saved it for this one or not. This one was, yeah, this one doesn't have anything in it. If your job script output file captures like the wall clock time and things like that, I will want to see those as well.
And if you're not running in a job script,
You
does
can
the
just capture standard out,
okay?
standard out.
So it's either the output from the job script, which is standard out,
Yep,
but just put in a file, or the standard out from the run.
yep. Here is stdio from a run, and there are a number of these are warnings that don't impact the model. And you'll see the same thing in the build. So for instance, let's see if, oh, it killed my history. Okay. So let me go grab. All right, you go out and do a git clone. It will create this directory and you'll get these files. Right, and you'll go through and set these things will already be set. You'll be able to change your processors, but we will set the grid size. We will tell you in this file, you can change this, you can't change that, so that you'll know which parts are actually a part of the simulation that we want you to run and which parts are open for you to change. The things that we will typically begin to change, and this is where, to answer your question a little bit more, Jeanette, these flags up here control what factors in the simulation may make it more complex, right? Rotational, magnetic field, things like that. We may turn those on and off. We may change the grid size and set some constants in such a way that the model gets way more complex. Right. So the
And you,
main. Oh, go
oh,
ahead.
I was going to say, and then back to that file really quick. So what the teams will change is really the NPEY and the NPEZ,
Yep.
which answers there's a question in the chat along those lines. So that's really, the teams will set that particular to their systems, but the rest of this file will probably be fixed.
Yep.
Okay.
Yeah, and what's set in the when they initially pull it down, these are set fairly low so that the teams can take this, hopefully build it, and run it, a very simple model, just to get a feel for how it compiles, how it runs, just a confidence builder that they're doing things the right way, and they're getting used to the code. This model with a grid size this small and this many cores should not take more than 5 minutes to run at the most on anything. Right, the other file they'll spend time in, like we talked about, is this one here. So for instance, I may come down here and say, you know what, we're going to run with 10 time steps, and I want you to dump your variables on every time step, right? And that's what that's going to do. Now, for me, right, so let me grab. So I need to, like, I just logged into this node. I need to load my environment. We use modules. You may load it manually or do whatever, however you want to manage your environment. But for me, I have to run these two things, which loads the GNU compiler and the MPI library built with GNU, right? And I need to make sure that my make file, the make file in the Git is pretty generic, and I can't type. There we go. Right. For this one, right, the teams will spend a lot of time in here changing this to suit their particular needs. That's all I need in here. All right, I've got my environment, I've got my make file, I can run make. Now it's gonna spew some warnings, but they can be ignored. Right, these are just warnings. But you see down here, it successfully completed its compile. To be honest, I could probably count on one hand the number of HPC codes out of the hundreds that I've built that don't spew some kind of warning. So don't be alarmed at that. So now we pulled a Git repo. We have edited the make file. We've edited the necessary param and set files. The other thing to note is that every time you make a change to param or set, you got to rebuild it because you're making changes in the source. So if I go in and I make another change, I need to do a make clean to remove these built executables and object files, and then rerun my make to build it again.
So just make sure I understand, the real challenge here is to find compiler flags to build this code the most efficiently for your machine. That's the challenge here.
Yeah, that along with, for your particular machine, how you lay out the processes on your particular cluster, right? It may not be this is a typical fluid dynamics code, so it may not be optimal for you to run a 128 process simulation on just 2 nodes, even though you have that many cores, right? This is going to get pretty chatty, and you'll need to find out that the teams will need to find that sweet spot between computational capability and inter-process communication. Um, you can starve this simulation easily, and by starve it, I mean you can give it way more processors than it needs, and sort of starve out the grid simulation. In which case it will run way longer than it needs to because its communications kind of taking over its time.
So this may be one of those lovely examples of code that more is always not better.
Exactly. No, this is absolutely a code where more is not always better. You can run it on too few, and it will take all of its time in compute on too few processors, or you can run it on too many processors, and it will either crash out or spin for way more time than it needs to doing communications. The other thing too is you may go in and decide that, hey, I don't need to dump my variables as often. I may give you a simulation and I say, hey, dump the variables every 2 iterations. But I also say in there, this is a variable you can change. So you're going to need to look and go, hey, you know what? I'm willing to risk it and dump only every 10, right? Or every 100, or maybe the model is super small and you think, hey, I can run this pretty quickly. I don't need to dump my variables every iteration, right? So that's another thing that they can tune, and given your cluster, how you're handling disk and IO will affect how this runs, right? If you're dumping every iteration, you may be wasting time that you don't need to, uh, depending upon the simulation that we give you. But we will tell you what you can and can't change. The majority of it is going to be how you lay out your processes and uh, and how often you dump your iterations.
And optimizing,
Right.
compiler flags, right?
Yep. Compiler flags. Uh, yeah, things like that. I had gotten a question, I think, emailed to me early on about visualizing the output. Uh, I have purposely pulled that out of the scope of the competition, but sometimes we've used this code for teaching in one of the classes, and sometimes the students go, what does this simulation actually look like? You can visualize it and build a nice animation, and I may build some of those as examples so the students can get an idea what they look like, but they don't have to build them themselves. We use a package called Vapor from UCAR or NCAR, but it's a process involving running the simulation, dumping all the variables out, then running the variables through sort of a preprocessor in IDL, a package called IDL, and then pulling them into Vapor. So it's a bit involved, and really I didn't want to worry the students with that. But I'll put some examples up. They can be quite stunning graphics. They just take some time to massage out of the data.
So there's a little clarifying another question about the output files. So if you see that in the chat there, you know that the number of output files is determined by the number of processors, as you pointed out. But I think you also mentioned that that's not the things you're interested in. You won't be interested
Right,
in those output files. There are other things that get outputted that you'll be interested in having them send.
right. The .list file is the main one. That's the file I'm going to ask for. That and your standard out. So let me.
But not those output files generated by
Right.
each process. That's not what you're
Nope.
interested in.
I'm not interested in that.
And also realize there'll be instructions for each of these challenges that you'll receive at the beginning of the competition, which will clearly lay out, what's what you're to turn in, what's the expectation from the judge. So you'll get detailed instructions about that
Yeah,
at the start of the
the
competition.
simulation when it runs is going to create these files. It's going to create this file and this file. And I am going to ask you to turn in, at the bare minimum, these two files and your standard out, which is whatever it spits out on the screen, whatever your scheduler captures as standard out. Those are the three things that I'm going to ask you to turn in.
I have a question. If teams make modifications to run the code on their GPUs, what do they need to watch for to make sure that everything is correct?
So on the GPUs, let's go to, so these numbers right here are excellent numbers to use for verification between simulations. These should always be the same for the exact same simulation. So if you want to verify, if you make a change to the code and you want to verify that your changes are reproducible and accurate, you can compare them to the unmodified code here. Now, I say that with a caveat that if you're going to make changes to the code, make your changes early and get them to me so that I can give them a once over. And to make changes to the code, I may ask the team, I would do this ahead of time and don't guess, because I may actually want to see this stuff here for changed code. I don't know anything about GPUs. It's not my area of programming. I know that they're awesome and they can add a lot of capability. I just we've not spent any time converting this code, and I don't know how it's going to behave on GPUs and what the factors are that go into porting a code onto GPUs. I would like some time to review that beforehand. So that's the only thing I would ask, is if you're gonna go that route, get me that as early as possible.
Thanks.
And I think that's fair, considering I am not the GPU expert. Right? What else? Let me look at the chat here. Yeah, I think we've covered these questions. Yeah, are there any other questions? Like I said, this is pretty simple, basic code. This is probably the simplest HPC code you'll ever run into.
I kind of like the dichotomy between impasse A and this code, where impasse A
Yeah,
is a lot more complicated. It's also a lot more, hand holding is the wrong word, but it's a little more, you don't have to understand so much about impasse A to actually run impasse A, where here you have to understand a little bit more about what's going on in the code and stuff like that to run it, right? So there's like these nice dichotomies of these two codes.
yeah.
Uh,
Some other fun things for students about this code is in today's world, you can go through a CS degree and never see Fortran. But when you get out in the real world, sometimes it's more valuable to consider what language it's written in as more of a tool than than anything else, and you can always learn to use a new tool, right? Fortran's just a tool. Once you get into it and dig around in it, it's logical, straightforward. You can pick it up pretty easy. Things make sense if you can program in C or Python or or any of the modern languages. You should be able to look at the Fortran code and at least make heads or tails a general gist of what it's doing. So this does get students a little bit more into the source side, and in many ways this code is closer to what, if you were to go through an undergraduate degree and get your degree and decide that you're going to go on and get an advanced degree, this is closer to something you might write fresh out of college than, say, a Wharf or a Games or a, whatever. So it's a little bit more graspable. There's only a few files. In an afternoon, you can go through and kind of skim through all of the source files and get an idea of what's going on. I would encourage the teams to go through the source files and kind of read through them. They're commented, and a lot of the comments are very valuable insights into what the code is doing where. So.
And although teams may not encounter Fortran in their, computer science, academic careers anymore, it's still all over the place at HPC. Fortran is still heavily used. So.
Yep, and all of your techniques for Jacobian distribution and things like that, they're all still in there. They're all those things you learn in a scientific computing class are in there. They're just expressed in a Fortran mode versus a C or a Python context. So yeah, that's pretty much it. Unless there are more questions, I'm happy to answer. This code has been run on Cray machines, on MIPS processors, on Cortex machines, on all kinds of Intel machines. The TAC systems, the NFS TAC systems in Texas, the DOE systems at Oak Ridge, and the Columbia Pleiades systems at NASA Ames. We have run this code on all of those resources. So, it has a fair amount of heritage to it. So yeah, that's my app.
Yeah, I don't see any more questions. So thanks so much, Doug. This is great.
Awesome. And I need to get Jeanette. I need to get sort of connected up with Discourse so I can follow that. But my email is also in the Git repo in the README. So you can always reach out to me there. The teams can always reach out to me there. I am going to be traveling, but I will always answer email.
Well, I was gonna look at that question, right? And I think, yeah, it's about, again, those process partitions, right? So the idea, I think their question was, about changing those two values, right? That NPEY and NPEZ values. I think that's what the question is. And because I said the recent commits have adjusted the process partition from 8x8 to 4x6. And so so that's I think that was that kind of the same question that was asked here in the chat that you can modify that partition settings. That's correct.
Yep.
And then those output files, those per process output files are probably not going to be something you ask for.
Nope.
So
I am not going to
that's-
ask for those.
Right.
In fact, you may know better than I do what the storage capabilities of the competition server where everybody submits will have. If I asked everybody to give me all of those files, we would probably max out that centralized server. So I do not want those .0 files.
Well, how big are they? How big are the ones that are
Well,
there?
they're going to get pretty big.
Again, in my world, you really have to define pretty big, Doug.
Yeah,
Pretty
no,
big means what I mean by pretty big is probably not what you mean. So, yeah, how big are
yeah.
these
So
files right here?
so these files, it's not uncommon for a decent simulation in a 512 by 512 by 512 to go 200 gig for one simulation, right? So when you multiply that by 10 or 12, however many teams we have, right? Yes, in yours and my world, that's not serious storage. In the little server that we bring to Cluster Challenge, if everybody is going to run 5 simulations and you dump 200 gig per simulation times, times 5 times 12 teams or whatever, then we might. And the other applications, I don't know what other people are asking for in their applications, but I don't need these. We don't need to submit them. If the students want to take these offline and go through the process of building a visualization, they're happy to. I will leave that as an exercise to the teams, but I do not need them. We don't want them.
Yeah, I mean, you probably don't want them, but I will say that, Doug, what we now have for the infrastructure is a per file system. We have a file server per team.
Oh, wow.
And
Okay.
each team has a terabyte of disk in the file system that we give them. So
Yeah, so we would be bumping, it's quite possible we would be bumping up against that terabyte limit if we
Yeah.
asked for these files from just the 3D MHD simulation. So that is why I don't want them.
I gotcha.
And I
it
would
might
tell
take a
the
bit.
team, oh,
Yeah.
sorry.
I was gonna say it
Uh,
might take a bit to copy all that data over to the file server too. So you
Right.
probably don't want 200 gigs of data from the teams.
And I was just about to say, as a general rule, take this as a longtime competitor wisdom for the teams. This advice would be: do not wait till the very last hour of the competition to submit your results for whatever applications you have.
Yes. Submit as you go. You can
Yep.
always continue to submit, right? We don't do anything with the data submitted until the end of the competition. So put what you can on the file server and change it as you go.
Yep.
As soon as you have a result, I would put it on in the output directories, and there'll be instructions on where to put things, but later. But I would copy it right to the file server and get it submitted right away.
Yeah. And that's a biggie. I have seen issues in the past where, for whatever reason, the teams have all waited until the last couple hours of the competition to submit, and then whatever happens, Murphy's Law, networking things, hiccups, whatever. And so I would just say you're better off submit early, submit often, is really the best course.
Yeah, that's fine advice. So we have a couple more questions that have popped up since we've been chatting there, Doug, in the chat.
So let's see here. I see one that says, can you briefly define an arctangent grid? Not briefly, no. Stephen might have a better concise definition for an arctangent grid than I do.
Yeah, or at least a reference. I've been trying to find that. It gets lost in a lot of other Google.
Yeah, I can
Okay.
definitely provide a a good explanation to that. It might
Okay.
take me a little longer than I have right now to write out.
Okay. Yeah, I think that would
In
be
fact,
interesting to know.
yep, let me stick that as a note. That's actually kind of a fun question, not a question I get. All right, and then the content in the .list file is related to in step 0. 3DMHC setf. Is this parameter specified in the competition? The in step 0, I will tell you if it's going to be a competition variable, but in step 0 is in 3DMH set, and we're going to go look at that. Where am I at? So you're asking about this one right here. I will tell you that that will probably be up to the students. You'll get to change that to whatever you want. This controls how often you dump those variables. I may set it, right? If I'm a particularly mean application judge, I may set it, but there'll be a comment in there that says, hey, you can change these things all you want. I may set it to something like dump it every time step, and you may get 1,000 time steps in and run your system out of disk space. And then you go back and look and go, why did this crash? Oh, because this is telling me to dump my stuff every time step. And if I look at the source, it'll say, hey, you can change this, right? But if you just build it and run it and blow past that, right? This is one of those things where I'm going to give you 5 simulations to run. And in the simulations, I will tell you in the comments, hey, you can change these things and you can't change, you can change these variables and you can't change these other variables. So you'll need to look at that. You know, I may give you a simulation and say, here's the simulation. Feel free to change your NP variables, right? How many processes you're going to set up, how you're going to set them up. And feel free to change the in step 0. But I may set those variables to something else. The idea is to make you go in and consciously understand making those changes in the source. And to understand their impact, right? Because I say you can change it, you may, if it's a large run, you may want to set that end step to 10. So that if for some reason, power outage, hardware failure, you don't lose 5 hours worth of compute time. That's a choice left to the team. Does that answer your question?
Can I give a slight tip that
Yeah.
you probably do want to have it set to a value that's at least not higher than the total number of steps, because you will need that final output.
Oh yeah, that's true.
And just as a general comment, so this is a code and a task that getting comfortable with tinkering with the source code is going to be important. In the sense of tinkering with these parameters and recompiling and, you know, looking inside the source code. It's not just a case of build it and run it.
Yeah. And Stephen may have a particularly good advice here, because you'd never seen this code before the competition, correct?
No.
Yeah. So this isn't a super popular code. This is a code from a very small group of solar physicists. And so Stephen has a fresh set of eyes to looking at this. So yes, he may see, he will see things in it that I don't, because I am a little bit used to mucking around in it.
All right, there's one more question there in the
So
chat.
we
So
must
let's time for one more.
So we must ensure that the modification in code won't change the dumped variables. Yes. And the variables that like I said, the variables I'm going to use for verification are those variables in the .list file, because those are some calculated results that for verification. But again, I don't need to see the .0 files. If you make, like I said, and let me clarify this a little bit. If you make changes to the code to try to put this into GPU, that I may want to see the .0 files to get full verification before the competition. I do not recommend waiting to the competition to try to convert this to a GPU code. Do not recommend that at all. Wouldn't recommend that for any code. I don't want you to make changes before. You should be comfortable in running this beforehand, and I don't want you to get to the competition. I don't want a team to get to the competition, make calculable changes to the code, submit their output, and then only come to find out that their output is wrong, and the simulation is incorrect and is producing incorrect errors. Right, there are instances where you can run this simulation and get incorrect results in some of the, especially diffusion and things like that, where the model looks like it ran just fine, but in the calculable results, something is off. So I would say, don't muck with the math. The optimizations, how you lay this out on your cluster, how often you dump time steps, being able to, having run this enough beforehand to be able to go, oh, he is gonna want, there's this simulation calls for 1,200 time steps. What does that look like running on my cluster? How should I lay this out? How many processes should I give it? If you do have a profiler, it may be worth looking at the memory to processor profile. It's pretty thin. You shouldn't have an issue with any of the cluster hardware that I've seen presented in the proposals. But that is another area where, if you really try to stack this densely, you may run into memory issues with trying to run other simulations at the same time as this on the same node. Right, so your RAM per process, you may want to watch that and see if there's an optimal spot for your machine.
All right. Well, thank you, Doug, for doing this.
Sure.
So this was great. And thanks everyone for your patience this morning with the confusion of the start time. So I apologize for that, and appreciate everybody's patience. So thank you so much, Doug. Do you want to stop the recording?
Yep.
All right.